Hi class, welcome back for the next section, chapter 1.3. Today we are going to be talking about algebraic expressions. Generally what this means is polynomials in this sense, although algebraic expressions can contain things like exponentials, logarithms, things like that, right? Square roots. So again, please remember to go through these lecture video series with something to write with and a piece of paper, something to write on. So keep your own notes as well as the notes that are provided to you so that you can have everything in your own words. Okay, so let's go ahead and get started. So a polynomial, okay, so if we break down this word, poly means many, nomial means numbers, right? Or in this case, we're talking about terms. A multi-termed system expression has the form as such, okay? an times x to the n, an minus 1, xn minus 1. Here, these n's are indices. They're telling you which term you're talking about. As you can see, we get from the abstract down to the concrete, right? This is the a2 term, the a1 term, the a naught term, or the a0 term. So notice that as my index decreases from n and then 1 less and then 2 less from the n that I have down to 2, 1, 0, so does the power that I'm talking about, right? I start with the nth power and I decrease to 1 less than that power and then 2 less from the first power. So it's going in a descending order from the greatest down to the least. And if you notice here, the index here is 0 and it's attached to an x to the 0 power, but we know anything to the 0 power is 1, so we don't have to write it, right? So we could actually write this as a0 x to the 0 power, but since we know what anything to the 0 power is, we don't have to write anything, okay? So this is going to be very important. Chapter 3, we talk about this in a lot of depth. Okay, so right now we're really just going to skim the surface and talk about how to do arithmetic on these things. And in chapter 3, we're really going to analyze these polynomials. Okay, so this first piece right here, a sub n, is called the leading coefficient. Okay, a0, this last piece here, is called our constant term. It's constant because it's a real value, right? It's a real number. It's not attached to any variable piece, so it's a constant term, right? All these other ones have a variable piece associated with the term. This one does not, so it is a constant. Okay. Each a sub I, where I is an integer, right? 2, 1, 0, so forth. Okay. These are called coefficients, right? N is my degree of the polynomial. Okay. Each of these terms, okay, so let me clarify that. Every one of these a sub i's, right? So I stands for just some regular index, right? It can be, if I is 2, I'm talking about the a2 term. If I is 5, I'm talking about the a5 term, right? So it's just saying that each of these a pieces are coefficients. A coefficient matched with its variable part is called a term. Okay, so from what we can see here, there's n plus 1 terms, right? Because I have 1, 2, boom, 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 up to n terms, and then one more. So every polynomial has n plus 1 terms. Okay. Again, each product, okay, product means multiply, right? The end result of a multiplication. So each product, so each of these multiplications, coefficient times the variable term piece, coefficient times the variable piece, each of these is a term, right? So your terms are separated by the plus signs, or sometimes they may be minus signs if our a sub I is negative, okay? So each of those is called a term, and we can describe a polynomial in multiple ways. One way to describe it is by its degree. An nth degree polynomial, a 10th degree polynomial, a 5th degree polynomial, okay? The degree will tell you how many terms it should have, right, in standard form. or we can just talk about its number of terms. I have a 3-term polynomial, 5-term polynomial. However, we have specific names depending on the number of terms. So if my polynomial only has a single term, okay, it's called a monomial, right? If my polynomial has 2 terms, it's called a binomial. See, mono means 1, or mon, I guess, means 1. Bi means 2. So if I have 3 terms, right? Trinomial. If I have 4 or more terms, we just call it a polynomial. Okay. So monomial, binomial, trinomial, that's what we call a polynomial that has less than 4 terms. Anything 4 or more is just a polynomial. Okay. Now again, these are polynomials. It's just kind of a standard notation, a standard verbiage to call it a binomial or a trinomial. Okay. When we add or subtract polynomials, we can only add or subtract like terms. Okay, so what does it mean to have a like term? It means that the variable part is identical. Okay, it doesn't matter about the coefficient, it's the variable part. The variable part has to be identical. So we saw this in the last section when we were talking about simplifying radicals. I could only add 2 radicals together if their radical parts are identical. Okay, because I have multiples of those things. Same thing here. If I have a bunch of x squares, I can just add up all the x squares and say I have this many x squares, right? So the variable part has to be identical. The coefficient tells us how many of those variable parts I have, right? So in this case, I have a1 amount of x's. I have an a2 amount of x squares, right? I have an a0 amount of constants, okay? So when I'm adding and subtracting polynomials, I'm adding up the like terms in that case. Very, very, very important. This is one of the number 1 things I find that my students do not do, and it really messes up their simplifications when they're adding, subtracting, doing arithmetic on polynomials. If you are subtracting 2 polynomials, okay, you are taking one polynomial and you're subtracting from that another polynomial, right? So remember what I said way back in the first video. We use parentheses to signify I have a quantity here. My polynomial is a quantity. If I choose an actual value for these x values and I do the math, I will get a number out, right? So my polynomial represents a quantity. So when I'm subtracting 2 polynomials, I'm taking one quantity and subtracting from that another quantity, right? So I want to make sure that I'm using my parentheses correctly, especially when I'm subtracting, because we know what happens when we subtract something that has several terms in it. I distribute a negative sign. So a lot of times my students will subtract 2 polynomials and they will not use parentheses and they will forget to distribute the negative sign, and now all of their arithmetic is messed up. So it's very, very important that when you're subtracting at any time, you use parentheses so that you remind yourself to distribute a negative sign. Okay, so let's talk about multiplying polynomials. When you multiply polynomials, we use the distribution property twice, right? Or what I like to call double distribution. There's other ways of multiplying polynomials that don't use this property. Lots of them are taught in high schools. In my classes, I don't really care how you multiply them as long as you're showing your work. I'm familiar with all the little box methods and the little diamond methods of factoring and all that kind of stuff. That I don't mind at all, okay? However, I tend to use, again, what I call double distribution. It follows the properties of algebra. It's not some little trick to use that just happens to work, right? So this is a method it will help you develop your algebraic skills, right? So this is what I tend to use. And obviously, as I go through the process of making these videos and I continue to use the algebra that I use, it's important that you're familiar with my methods I'm going to use so you know what I'm doing, right? So again, if you have another method that you're familiar with, you can go ahead and use that on any exams and tests. However, right, as we go through these lectures, this is what I will be using. So The way that this works is you just distribute one polynomial across another, and then you distribute those single terms across the polynomial that you just distributed. It's actually very easy. We just do this term by term. Okay, you can distribute in any way that you want. You can go the left across the right polynomial, or you can go the right polynomial across the left. Okay, I tend to just go in the same direction that I read. I take the one on the left and I distribute across the one on the right. Okay, so I will take this polynomial and distribute it across each of these terms. I could do the opposite. I could take this polynomial and distribute it across each of these terms. Okay, it doesn't matter which direction you go. That's the beauty of this. Everything ends up multiplying against everything else. Okay, so again, it doesn't matter which direction you go, but I just take the one that comes first and I distribute it across each of these terms. So what does that mean? I take this whole thing and I multiply it times x4. An easier way of thinking about that is that the x4 is just going to be on the outside of this polynomial. Okay. Then next I have to take this polynomial and multiply it all against negative 3x squared. So that's going to look like this, minus 3x squared times my polynomial. And then I do the same thing here. I'm going to distribute this across the 1. It just looks like that, right? So here you can see my second polynomial term by term is on the outside. And then this polynomial is on the right of each individual term on the inside here, right? So x4 minus 3x squared and 1. And then next to all of those, we have the first polynomial. So the next thing I do is I just take the x4 and I distribute it across each term. Negative 3x squared across each term, and this 1 across each term. Now again, what I said is you can do this the opposite way. I could have wrote this as 4x cubed times this, minus 2x squared times this, plus x times this, minus 5 times this. It wouldn't matter because everything multiplies against everything. Okay, so here I've distributed the left across the right. Okay, so now I'm going to distribute this x4 against these 4 terms. So we have 4x to the 7th minus 2x to the 6th plus x to the 5th minus 5x to the 4th. Then I'm going to distribute this with the negative, so it's going to change all the signs. So this will be negative 12x to the 5th, 6x to the 4th being added, right? Negative 3x cubed plus 15x squared, and then distributing this 1 doesn't change anything, so I just add that whole polynomial back across. Right? So now I have this very long expansion here, right? This is the expanded form. So I'm going to look and combine all of my like terms. I'm going to look at the x7s and add all the other x7s to this. There are no x to the 7s, right? I'm going to look for all the x to the 6 terms. There are none. Okay, so then these two are going to stay the same. I'm going to look for my x to the 5th term. So I have 1, 2 here. So when I add those together, I'll have a negative 11. Okay, so the 4 stays, the negative 2 stays. For the 5th, there's only these two to the 5th terms. So negative 11. So for my A4 term, it will be what happens when I add all of the coefficients that are attached to an x to the 4th term. And so there's just these two, so negative 5 plus 6 gives me a positive 1. I'm looking for all of my cubes, right? So that's just these two, so that's plus x cubed. And for the squares, I only have these two, right? Everything over here has already been used. So these are my two x squared terms, so minus or plus 13x squared. And then this is my only x term and my only constant term. So notice we go in descending order. 7, 6, 5, 4, 3, 2, 1, and 0. Okay, it won't always work that way. Sometimes there may be missing terms because things add or combine to 0. So this is a 7th degree polynomial. 4 is the leading coefficient. Negative 5 is the constant term. The A4 term is 1, right? The term that's attached to x to the 4th. The A6 term is negative 2. The A1 term is 1, so forth. Okay. Let's see. So notice also again that since n equals 7, there are actually 8 terms, right? 7. Let's start here. So there's 1, 2, 3, 4, 5, 6, 7, plus the constant term means that there are 8 terms. Okay. Special product formulas. So these are results that happen all the time from factoring, or I'm sorry, from multiplying. They come across so often that we just try to memorize the forms of them. We don't have to memorize the forms, but it just makes things easier when we do. Okay. So the first are, let's assume that a and b are real numbers, okay, or their own algebraic expressions. As we saw in the last video, we had actual algebraic expressions for a and b when we did this form, the difference of squares. We were using the radical conjugate, and a and b were radical. They were their own terms. They weren't just single numbers, right? They had x's and y's and z's in them. Okay, so they can be their own expressions or they can be numbers, right? It's actually the same thing. So if I have the same term but the difference in the middle is the sign, I can multiply those out and get a squared minus b squared. It's a very, very easy thing to remember. It makes math go a lot easier when we remember this special product formula. That way I don't have to multiply this out every time using double distribution or FOIL or what have you, right? If I have a plus b squared, this can also be a minus b squared, okay? Then what happens is it takes the form of a plus b times a plus b, or a minus b times a minus b, depending on what our sign is. It is not a squared plus b squared. That is the number one mistake that I see here, okay? You are squaring this quantity, so that means you take this quantity and you multiply it times itself twice. Okay, very important distinction. I see in calculus 3, I'll see this mistake where this will be something that students will have to do, and they will write a squared plus b squared. That is not the correct value. Okay, so this is the form that it takes, and it has its own special expansion. Okay, so most people will just remember this and write the expansion. So again, I wrote this to clarify that that's what this looks like. This is what you're doing. You're taking this and multiplying it twice, right? So the expansion is a squared plus or minus, right, depending on the sign you're using, 2 times ab. This is always going to be positive. This plus b squared, it's always a positive, so that's why I don't have to put a plus or minus here. However, this second term is going to vary depending on if this is a positive sign, it'll stay positive. If it's a negative sign, it would say negative. Okay. Now, if I have a cube term where I have to do this 3 times, okay, then its expanded form is a cubed plus or minus 3a squared b. This is always a positive, okay, and the squared term switches from the a to the b here. And then the last term, b cubed, is also plus or minus depending on what your sign is here. Okay, so now let's talk about factoring, right? So factoring and multiplying polynomials are opposite operations, just like adding and subtracting are opposite operations, right? If I have two numbers that I add, I can undo that addition by subtracting. Same thing if I subtract two numbers, I can undo that with adding. Factoring and multiplying works the same way, okay? Just like multiplication and division. Those two operations undo each other. That's why when we talk about PEMDAS, addition, subtraction is the same thing, and multiplication and division are also equal in the order of operations, okay? I've said this before, but subtraction is the same thing as addition, and division is the same thing as multiplication, okay? If I want to subtract two numbers, I'm really just adding negative numbers, right? 2 minus 3 is really 2 plus the value of negative 3. A subtraction is really just addition. Multiplication and division are the same thing as well, right? 8 divided by 2 is really just 8 times 1/2. Okay, so you can think of these things as the same thing, This is also the same thing with factoring and multiplying. They kind of undo each other. They're opposite operations, but they have similar forms, okay? So if I want to take two binomials, okay, and multiply them, I will have their expanded form. If I take their expanded form and I factor them, I now have them in their factored form, right? So the process of factoring is fairly easy, but you have to be familiar with it, okay? It's more than just, oh, I'm going to factor these two things. There's sort of a process to it, right? There's a hierarchy of what you kind of approach first. So the first thing you want to look at is always the GCF, right? What is the greatest common factor? Is there something that is a common term in every single term that shows up in my polynomial? So we saw this in the last section when we were doing the radicals. When we try to simplify the radicals, we're looking if there was something common that I could pull out in my final expression to turn it into a nice factored form. So we're always looking for a GCF first. If we can pull out a GCF, then what's left over on the inside of our expression, right, inside the parentheses, will always be easier to factor. So we always look for a GCF first. It just makes things way easier as we progress through the hierarchy of steps of trying to factor a polynomial. Okay, the next thing I want to look at is the number of terms. Okay, the number of terms is very important to me. Depending on how many terms I have is going to determine the method that I'm going to use to try to factor. Okay, if I have 4 terms, okay, if there are 4 terms, I'm going to start with trying to factor by grouping, right? So factor by grouping means I take my 4 terms and I kind of split it right down the middle. So I have 2 terms on the left side and 2 terms on the right side. After I split it in half, I'm going to factor out a GCF from both of the halves that I just separated. So I separated my 4 terms into 2 and 2. And I'm going to look at the first 2 terms, right? I'm going to think of that as a binomial. And I'm going to try to factor a GCF out of it. On the right half, I'm going to consider that as another binomial at this point. And I'm going to try to factor out another GCF, okay? I should be left with a common binomial term, okay? So on my left side, I should have a binomial, and on the right side, I should have the same binomial, okay? If I have the same binomial on both the left and right side, I can then factor that out as what I call a binomial GCF. So it's a GCF, but instead of it being a single value, right, like 2 or 3 or something like that, it is now a binomial. It is something like x plus 1. So I can factor that out, and I now have factored my 4-term polynomial. Okay. If I have 3 terms, okay, the method that I use to factor something that has 3 terms really depends on the leading coefficient. If the leading coefficient is 1, it's much easier to factor. Basically what I do is I look at the last term, A0. Okay, so here's just a little definition. If the first term is 1, we call it monic. Okay, it's called a monic polynomial when the first term is 1. So the leading coefficient is 1. You don't see a number there. It's just x to the 3rd or whatever in front. It's called monic. If our polynomial is monic, it's very easy to factor. It's what you've learned your whole life in high school and middle school, right? You look for the last term, the constant term. You split that into its factors. And you look for the factors that you can use to add or multiply to be the middle term. Okay. So factors of A0 that add or subtract equal A1. Remember, A1 is that middle term. It's very easy to do these ones. Okay. Now, if our polynomial is not monic, right? If we have a leading coefficient that's not 1, there's a couple of ways to do this. Okay, you can come back and do a factor by grouping. You can turn it into a 4-term polynomial. But my colleague, my office mate, has a really unique way of doing it. She calls it the Asian way. I'm not trying to be racist or anything. That's what she calls it. She's Korean, and it's a very, very useful method. I like it. I've used this method over the traditional methods that I've learned in school. I like it. It goes way, way, way faster. Okay. I call it Professor Choi's method. She's the one who showed it to me, so I named it after her. Okay. The last step is to make sure that you are done. Okay. So a lot of times there is more factoring to do. Okay. I should probably add in a 2.3 here. If there are two terms, right? If it's a special form, then you want to use one of these special form rules. Okay. So for instance, if this would be the only two term that you can solve. If you have a perfect square minus another perfect square, sometimes this might be a to the fourth minus b to the fourth, for instance. Okay. Or a to the 16 minus b to the 16. So there's special forms here that you can use that you also have to look out for. Okay. And that's part of the make sure that you're done. Okay. Sometimes there's more factoring to do. Have you completely factored everything, right? And if you haven't, then continue to factor until there's no more factoring left, right? So let's go ahead and do a couple of examples, and then we're pretty much done with this section. All right, so let's go ahead and factor the following. So let's start with 8. So we have 8x cubed plus 16x squared minus 2x squared minus 4x. So we could try to combine these two terms since they're like terms, and then go ahead and factor using Professor Choi's method or whatever method you may already know. But it's already in 4 terms for us, right? So let's just go ahead and utilize the first thing that we have and try to cut it in half and look for a GCF from both sides. But before we do that, we always want to look for a GCF of the entire polynomial. So if you notice, every single coefficient here is even, right? So I can pull out at least a 2. The smallest term is a 2, so I can pull out a 2. I also have an x in every single term. So I should be able to pull out a 2x, okay? So when you do this, you're really dividing inside each of the terms by 2x, right? 8 divided by 2 gives us the 4. 16 divided by 2 is an 8. 2 divided by 2 is 1. 4 divided by 2 is 2, right? So the 2 is on the outside. If I'm dividing by an x, because that's what I'm pulling out, then it's just like when I have x cubed over x, right? I have 3 on top, 1 on bottom. 3 minus 1 is 2. I'm left with 2, right? So I'm subtracting 1 from each of these. So this goes to 2, this goes to 1, 1, and there should be no x terms left over, right? So from here, we're really just going to focus on the inside. You can continue to drop down the 2x with you the whole time. I suggest that you do that because a lot of times students will focus on the inside parentheses, the inside polynomial, and they'll forget about this 2x. And at the very, very end, they forget to bring it down. They have this factored correctly, but they don't have the GCF on the outside in its factored form, right? So I suggest you bring the 2x with you the entire way. As such, right? So what we're going to do is we're going to split this in half. So I'm just drawing a straight line. Generally, I use a dotted line, but this is, I mean, obviously you see this is all in print. So I can't do the same things I would do if I was handwriting this, but it doesn't really matter. I'm just splitting this in half. So I have the 4x squared and 8x on one side, the negative x minus 2 on the other side. So when you split it in half, the third term should keep the sign that it has, right? So this is a negative. I'm not going to draw the line in front of the x and keep the sign on the other side, right? So the sign needs to stay with the term that it's with. So this is where the line is drawn. I'm going to look for a GCF from both halves. The GCF here, both of these are multiples of 4. They both also have an x, okay? On the right side, there's not really anything going on, but they are both negative. So I can pull out a negative 1. Okay, so I have my 2x that's still there. From this term, I pull out a 4x. What's left over is x plus 2, right? 4x goes into this, gives me an x. 4x times 2 gives me 8x. Here I can pull out that negative 1. Some students like to write -1. I never write 1 if I don't have to, so I'm just pulling out the negative, but know that there is a 1 right here. This is considered a -1. Okay. Now what we want to notice here is that the binomial parts inside of here are identical, right? That's going to be my GCF, my binomial GCF that I was talking about up here in 2.1b, right? Factor out the binomial GCF. So that's my binomial GCF here. Is this x plus 2, because it's the same term, right? So notice that the binomial parts are identical. If this was, for instance, x plus 2, and this was x plus 1, first I would want to make sure I didn't make a mistake somewhere, okay? But if I'm confident that I didn't make a mistake, and the two binomial parts are not the same, okay, then this would be prime over the rational numbers, meaning that it would be non-factorable, okay? So if I want to factor out my GCF, notice that if I pull out an x plus 2, I'll have 2x. I'm pulling out x plus 2 as a GCF, and I'll be left with 4x minus 1. That's what happens if I factor out x plus 2. Okay. So again, if I were to distribute this x plus 2 across this second term here, it would look like 4x times x plus 2 minus 1 times x plus 2. Again, that's why I was saying here about this double distribution method that I tend to use here. Okay, it's useful for you to understand some of the algebra that's going to be happening later on in the course. That's why I don't use the box method or the diamond method for factoring or anything like that, because this distribution of polynomials shows up later. Okay, not just here, it's useful in other places as well. Okay, so again, this is pre-calculus. We're trying to get you guys ready for calculus. So some of the little non-algebraic kind of cheats that we have, they're useful. They're not bad. I'm not, knocking them at all. But it is important for us to get used to the algebra for the algebra's sake, because there's things later on that rely on those, okay, on these methods. So for B, we're going to have x squared minus 7x minus 12. So this is a trinomial. There's 3 terms, okay. It's monic, right? The leading coefficient is 1. We don't see a number here, so that number is intended to be a 1. There's only one x squared, okay. So in order to factor this, this is one of the easy ones. We're going to take our a naught term, our constant term, and we are going to factor it. And we're going to look for the factors of 12, the pairs of factors that we can use to add or subtract to give me a -7. Okay, so again, we're now on the 2.2 part A. All right, it's a monic 3-term polynomial. I need the factors of the constant term that add or subtract to equal that middle term. My middle term in this case is -7. Remember, that sign is always attached. Okay, so first thing we're going to do is we're going to list out all the factors of 12. You've probably already done this in your head. If you're in this class, you've probably done this lots and lots and lots of times. Okay, but again, this chapter 1 is a review, so I'm assuming that some people haven't done all of this stuff or are rusty. So I'm just looking for the factors of 12 that add or subtract to -7. So ideally would list all of these out, but maybe you already know what they are and you've already factored this, okay, and that's fine. So just bear with me or fast forward. So we have 1 and 12, 2 and 6, or 3 and 4. So these are the 3 sets of factors that we can use for 12. There's no way for me to add or subtract 1 and 12 together to get -7. There's no way for me to add or subtract 2 and 6 together to get -7. 3 and 4, I can add or subtract in some way. Okay, so in order for me to do that, I would need a -3 and a -4 in order to subtract those. Okay, the only factors I can add or subtract is 3 and 4. Right. However, there's a problem here. Okay, if I use both -3 and both -4, when I multiply these, they would become positive. But I have a negative 12 here, right? So these two last terms, they need to multiply to give me my value here. So since this is negative, one of these factors have to be negative, okay? But that's not the case here. I don't have one of them being negative if I need both of them to be negative. So there's an issue, right? And the issue is that this is not going to give me a negative 12 when I multiply them out, okay? So negative 3 times negative 4 is 12. Positive 12, right? Not negative 12. So this is not factorable over the integers, okay? So for the next one, we have a non-monic trinomial. So we're going to use Professor Choi's method, okay? Basically what we do, okay, is we are going to factor the 6. We're going to factor the 5, okay? So for 6, we can factor this to 1 and 6, or 2 and 3. 5, we only have 1 and 5, okay? So I kind of have to show everything at once. So I have 2 and 3, and I have 5 and 1, okay? Now what we're going to do is we're going to multiply across, right? And we're going to multiply across. So 2 times 5 is going to give me 10. 3 times 1 is going to give me 3. Those results that I have, I need to add together, okay? And if it adds up to the thing that I have on the inside, then I'm good, okay? Now 10 plus 3 is 13, and if I make 10 negative and 3 negative, that will give me a negative 13, right? Which is what I need. So in order to make this a negative 13, you know, to add these together, whenever I change this to a negative or this to a negative, I apply that under the factors for the constant term. So that would make the 5 negative and the 1 negative. However, if I do that, I run into the same problem I just had in the last example. Negative 5 times negative 1 would give me a positive 5, right? So that leaves me with an issue. That means that the factorization that I have here, the factors that I chose, 2 and 3 for 6 and 5 and 1 for 5, are wrong. Okay? We have a problem. In order to add our products on the end to have a negative 13 to match what is in our polynomial, okay, we would need both of the 1 and the 5 terms to be negative. Okay? But again, negative 1 times negative 5 is 5, but what we have is a negative 5 in the last term. So I have an issue. So that doesn't mean that this is not factorable. Okay? It did mean that for the first one, for B, because it was monic. I ran out of options. There was no more options for me here. Okay? Here, this is sort of a trial by error, although it's very easy and very quick to find the correct set that works. So what we can do is we can take this and we can try to flip it around and write 1 and 5 instead. The problem is if I go 1 here and 5 here, I'm going to get 2 and I'm going to get 15. Actually, that might work because 2 and 15 I can make into 13. So let's do that, right? Let's switch our factors around, right? If switching our factors doesn't work, we would try a new set of factors. Now 5 and 1 doesn't have any more factors for 5, but 6 would. I could try 6 and 1 instead with the 5 and 1 and swap the orders around and see how it works. However, switching the 1 and 5 here might work for me. So I'm going to start with the 6x squared minus 13x minus 5, my polynomial. Instead of 5 and 1, I'm going to go 1 and 5, right? So here I'll have the 2 and 3 in the same place. I just switch one of them, right? So here instead of 5 and 1, I go 1 and 5. 2 times 1 is 5. 3 times 5 will give me 15. And when I add these together, I can do this in a way to get me a negative 13. In order to have a negative 13, one of these has to be negative. I have to have the 15 be negative, which means that the 5 would then be negative. Okay? So this works if the 5 term is negative. and all of the signs are then going to agree. Okay, so what I would do is I would change this to a negative, and then my factor becomes, these are all my x terms, these are all my constant terms. So 2x minus 5, 3x plus 1. Okay, 2x minus 5, 3x plus 1, because the 5 has to be negative. That is the Professor Choi's method of factoring. I've looked online and tried to find other names for it. I've heard the star method. I've heard the Chinese method. Generally, this is taught in Asian countries, I believe. So every term I found online had an Asian name attached to it. So I don't know what the actual appropriate method or name for the method is. So again, I'm just naming it after my office mate, Professor Choi. It's her method. So if you have to rewind that to see how that works again, then that's fine. Replay that one more time. But again, you're really just going to switch one factor. Okay, if this didn't work, then I would start over. I would have 5 and 1, but instead of 2 and 3, I would choose 6 and 1. Right, and that I know that would be a bad choice, because if I had 6 and 5, I would have 30, and then 1 and 1 would be 1. There's no way to get negative 13. So off the top of my head, I would know that 6, 1 and 5, 1 would be a bad choice. Okay. Now maybe 6, 1 and 1, 5 would work, but that would give me a 6 when I multiply across and a 5 when I multiply across, and I'm not going to get to 13. So right away, I know that that would be a bad choice, right? So you kind of have to use some intuition of your number sense to use this, but it goes really, really fast, right? You can kind of look right away and say, oh, that's not going to work too well, okay? But 2 times 5 is 10, 3 times 1 is 3. I can get 13, but the signs would have to not work in that case. So that's how I know that that doesn't work. So I just swap 1. Okay. Now let's say I decided to keep the 5, 1 here. If I swapped 3 and 2, I would have gotten the same thing. I still would have had, if I had this as 3 and this as 2, I still would have got 3 times 5, like here, right? And I still would have had 2 times 1, like I do here. So it doesn't matter which one you hold fixed and which one you swap if your first try doesn't work out. Okay, so it's very, very nice method. Just make sure that after you do the multiplication across, you try to, and you add everything together, you make sure that your signs that you need here agree. And if you have to make one of these negative to make it work out to be this middle number, it applies to the constant term. You do not apply it to the x term. So again, these are the factors for x's. These are the factors for the constant. That's why when you multiply this, this is really a 2x. Okay, so you can think of this as this is 2x and 3x. This is the constant 1 and the constant 5. And these are the arrows. The diagonal arrows is the ones that go across to match up. So 2x and, in this case, a negative 5, 3x, and a 1. Because again, you're factoring this, right? 6x squared factors to 2x and 3x. Okay. So we have one more example. Okay. As you can see, it's much more difficult than what we were working with before. However, this is definitely something that you would see in a calculus class. Okay. So again, like I said in the first video, we're going to kind of step up in intensity in the way that I show you things in this class. Some things will be easy, and some things will be more difficult. Again, I'm thinking of this as a review, but I want to do this review in the lens of pre-calculus, right? I really want to get you guys ready for calculus. That's the purpose of this class. But again, we need to review your algebra, right? So I say this to my calculus students all the time. The stronger your algebra is, the easier calculus will be. Okay, so calculus introduces a lot of new ideas and methods and ways of thinking about things. But there is a ton of algebra. Okay, so if you have very, very strong algebra, calculus is a breeze. The concepts of calculus are not that hard to grasp, but the math, the algebra that goes with it can be very, very tedious, very long, very difficult, right? So again, strong algebra leads to much, much easier time through calculus. Okay, so we're stepping up a little bit. Notice that this is not a polynomial. Okay, a polynomial does not have fractional exponents. Okay, This algebraic expression, however, does have three terms. Remember I said terms are always separated by a plus or a minus sign. It's a set of multiplications and then an addition or subtraction, and then a set of multiplications and then addition or subtraction. Okay, so here we have 1, 2, 3 things being multiplied: a coefficient, a variable part, and then a binomial part raised to an exponent, separated by a sign, and then another set of multiplications, a sign, and another set of 3 multiplications. So there are 3 terms here, okay, and each of these terms have 3 products in them: a coefficient, a variable part, and a binomial part raised to some power. Now, if I were to give this to you right away, maybe your first thought would be, oh, what the hell is this, right? I'm going to just expand everything I can and then try to simplify everything from there, okay? You can't do that. You can expand this and turn this into 2 more parts and then have 4 terms, but that's actually not going to help you at all. That's going to be actually detrimental to your trying to solve this, because you can't expand any of these other parts, okay? If you notice here, this is raised to a power, okay? This is raised to a power. However, this is a binomial. You cannot distribute this power across your binomial, even if it does have the same power. It doesn't work that way, okay? Actually, I think you can if it has the same power, but we're not going to do that. Actually, no, you can't, okay? Apologies. Rewind that. If you have an exponent, you have to deal with the exponent before you can distribute any sort of factor on the outside, okay? I cannot distribute this x to the 3/2 across this because I'm raised to an exponent. The exponent is like a guard, right? It's PEMDAS. This happens first before any sort of multiplications. So you can't simplify this by expanding it. You can't expand this at all. You can on this part, but not these, because there is no exponent here, okay? Notice, however, that we do have things in common. All of these have a coefficient, okay? All of these have a variable term, even though they have weird powers, and all of these have a binomial term of 2x minus 1. So we have a GCF here that we can pull out, okay? Now, the question is, what is this GCF? Well, you have 2/3, 1/3, and 2. So now you might be saying, well, there's no common factor here. That's fine. There doesn't have to be a common factor, okay? We're going to pull out a common factor that's going to work for us. We're going to pull out the fractional part. We're going to pull out the lower fractional part, the 1/3, not the 2/3, because that will mess up this one. We're going to pull out the 1/3. We're going to pull out a factor of 1/3. Okay. So next we need to look at the x. Okay, x, I have a 3/2, a 1/2, and a square. So remember what happens when we pull out a factor? We end up subtracting all the other exponents by the degree of that factor. So if I pulled out a 2, I'd have 1/2 minus 2. I'm still going to get a fraction. 3/2 minus 2, I'm still going to get a fraction. If I use 3/2, I'm going to get 1/2 minus 3/2. 1/2 minus 3/2. That might work out to a whole number. I don't feel like doing the math right now, but I know for certain that 2 minus 3/2 will not. Okay, so what we're going to do is we're going to pull out the 1/2. Basically what we're doing is we're going to focus on this term here, okay, and we're just going to factor this whole term. We're going to try to make this 1. Okay, now I could try to make this one and it'd probably work out for me, okay? I would not want to work on this one, because if I'm pulling out the value of 1 here, that's not going to really help for these fractional exponents, right? But if I pull out a fractional exponent, since I have more fractional exponents, I can get most of these to turn into whole numbers, and I just have 1 fractional exponent left. However, if I pulled out a whole number, right, a 2 and a 1 here, and this 2, I'll be left with a bunch of fractions left over. I'll have more fractions left in my factored form than I would here, okay? So that's what I'm going to do. I'm going to pull out, I could have done 2/3 and 3/2 and negative 1/2. It's probably going to be easier if I just keep everything positive and this as a simple 1/3. So I'm going to pull out 1/3, I'm going to pull out x to the 1/2, and I'm going to pull out this binomial term as well, right? So we'll start with the first one. Pulling out a 1/3 is like multiplying this times the reciprocal, right? Because it's like fractions. So 2/3 times 3 leaves me with a 2, which makes sense if you think about it, because what times 1/3 is 2/3? It's 2, right? Here I'll do a subtraction. 3/2 minus 1/2 will leave me with 2/2, or 1. Okay. This binomial term, I'll subtract the powers. Negative 1/2 minus 1/2 gives me minus a minus, right? Or a negative 1. This I chose as a factor. So this will turn into just a single minus 1. Okay, because I've pulled out this whole thing. So this thing divided by itself is 1. So I don't have to do any fancy math here because I'm basically dividing this by itself. Okay. Here I need to do the same thing. To figure out the coefficient, I can multiply this by the reciprocal. So that's going to jump up to a factor, or I'm just going to jump up to the value of 6. Okay. 2 minus 1/2. So this is going to be 4/2 minus 1/2. So that'll be x to the 3/2. And here I'll have 1 minus 1/2. So that'll be 6x 3/2, 2x minus 1 to the 1/2. Okay. And so from here, basically all I'm doing is I'm rearranging everything so that it's kind of in order. Ideally, I would really want to put it in descending order, so maybe this term would go first, but at this point, it doesn't really matter, right? I just really want to put the constant at the end because it doesn't fit in with everything else, so throw it at the end, okay? Now, if I wanted to, I could try to factor the inside a little bit more. I mean, it's not a perfect trinomial. We're not going to get, this is not going to be very clean. This is as far as we can get, right? You pulled out a GCF to make this a little bit nicer. I could try to factor this part a little bit more and pull out a common a 2, an x to some power, and another 2x minus 1. But this will still be a negative 1. There's really nothing for me to do here. So it's really easier just to let me leave in this form, okay? So that's it for the section. I will see you in the next one. Thank you guys.